The very first effort to come up with a hypothesis test, with a procedure of multiple hypothesis test that takes all the hypotheses together, was made by R.A. Fisher in his famous least significant difference test, LSD test. And in this test, he proceeded like this. So I will illustrate this with an example of a linear model. Suppose we again work with our same familiar setup where we have got a single factor input and the model is Yij equal to mu plus alpha I plus epsilon ij with the usual Gauss-Markov assumptions. And we are trying to test that all the alpha i's are same, and we have split it up into component hypotheses. P choose 2 of them, and we are trying to perform multiple hypothesis tests. Now what Fisher suggested is something that is very common sense thing. If you think about it for some time, you will yourself come up with the same idea. He said that since I already know how to test all these things together, why not carry out that test first? So what he did was, he said that I will proceed in 2 steps. In step 1, you just carry out our familiar test, namely the test where you are just testing alpha 1 equal to alpha 2 equal to etc. So basically you are testing this model against the model Yij equal to mu plus epsilon ij, the test that you have already learned about. If this test accepts, in that case, you just say accept, accept, accept for each of those k many hypothesis testing. So instead of just saying accept, he says accept, 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 accept for each one of those component hypotheses and stop. If, however, you reject this overall test, then you move to the next thing. And the next step is, again a very common sense one, you pick up 2 things. So one S and one T, and now you compare between those 2 things using just a 2 sample T test. And if you want, you can even test directional things like alpha I greater than alpha j. You can even test that. However, with a little difference, and the little difference is that here, when you are using a t-test, you need some estimate of sigma square. Now, when you are carrying out our usual 2 sample t-test, what we do is that there are actually different situations. You might say that both the sigma squares are the same, or they are different. Depending on that, there are different variations. In this case, we are of course in the homoscedastic situation. So the natural technique will be to use the pooled estimator of sigma square, pooled based on those 2 samples that you are comparing. But here Fisher suggested we already have one estimator of sigma square based on the overall data. So that is important. We already have one which is based on the overall data. So if we have that, use that all the time. So even if you are comparing alpha 1 with alpha 2, instead of considering sigma square estimated from only y1j's and y2j's, you consider sigma square estimated from all the yij's, even when I is not equal to 1 or 2. So that is what Fisher suggested. And then based on that, you give accept or reject verdict for each one of these things. So it is a 2-step procedure. To see that it really satisfies that family-wise error rate condition, that is very easy, because the very first step guarantees that. So if you make even one false discovery, how have you made that? Obviously by moving to step 2, because in step 1 you are not rejecting anything at all. You are never declaring any discovery at all. So no question of false discovery. So false discovery can come only from step 2. Step 2 means you have already rejected that overall test which you have carried out at the same level as your FWER. So if you wanted to have FWER less than equal to 5%, you have carried out that step 1 at 5% level. So the very fact that you have rejected that means you are already in a subset of probability less than or equal to 5%. So whatever you do in step 2 can never increase that probability. So the presence of the first step itself guarantees that the family-wide error rate is controlled. So this is called Fisher's least significant difference test, and as I said, it is the simplest way of incorporating all the hypotheses simultaneously. However, it has some drawbacks. Number one, its power is not very good, and number two, sometimes it provides with counterintuitive result. Excuse me. One example being like this, that it is possible that you reject that overall test at level 1. So you expect that I am not going to write accept everywhere. I am going to have at least one reject. But in step 2, you end up accepting every one of those component hypotheses. So you really finally end up saying accept everywhere. And that may happen because in this case you are using sigma square hat, which is actually based on the overall data. So such weird behavior occasionally happen in case of the situation being borderline. But other than that, it is a very simple, intuitive, and naive way of approaching the problem.